want to learn shader nodes? I know shader nodes. In this video, I'm going to teach you what I know. It's going to be fast, so if you can't hang, slow it down, but we're going from nothing to everything. Here we go. This video is sponsored by Skillshare, and we're going to talk about that in a bit. So in Blender, when you're doing shading, you go to, surprise, surprise, the shading workspace, and this is where we do our work. A object inherits a material, and what we do in the material is reflected in the object. So if I get rid of everything and maybe put down a plane, I can give this a new material where I'm going to call this teaching you, and then anything we do here is reflected on that object. And of course, if I add another object, it can inherit the same context of material, and then this changes both of them, okay? So objects inherit a material. For most of this course, we're just going to be using a grid because it's easy to visualize, so make sure you're either in look dev or rendered mode. I'm mainly going to be in look dev, and we're going to look from the top view. And let's kind of expand this so you can see what we're doing the whole time. So as you can see, we have a default node setup with this weird node called the principal BSDF, but what matters is that that is piping into the surface of the material output. If I get rid of this, it's going to be black because nothing is piping into it. If I do this, now we're going to have something piping into it. I can create a different node, maybe this one's going to be red, and now we can switch between the two. So without knowing what this means, all you need to know is that a link sends information into the surface of the material output. We'll talk about volume and displacement. The simplest thing we can plug into the surface is just a number. So Shift A to add nodes. I'm going to type in value. You're going to learn the names of these as we go. Connect this to this. By the way, if you're wondering how I do all these like quick things, there's an add-on called Node Wrangler. So in add-ons, type Node Wrangler and enable it. There's a lot to learn with it, but basically you hold down Alt and right-click drag to do surface, Control and right-click drag to cut, and then there's a few more. So we connect the value to the surface, and you can see as I change this, it is going to change the brightness of the thing. A value is just a number where 0 means black and 1 means white, and then 0.5 is gray in between. And it turns out you can actually go above 1. So if I make it 10, you can see it's actually noticeably brighter. And it turns out you can also go negative, but that's still going to look like black because anything below 0 is going to look black. But it is actually storing this number where we can add in a math node, which we'll talk about in a second. I can multiply by -1 and we get white back because -1 times -1 is equal to 1, which means this must be storing the value. By the way, I like using snapping here to make sure that everything I do is in this like nice grid where, everything's organized. As you might expect, we can take values and add them together. So we can have different nodes with different values. Our next most important node is the math node, and this is how we combine them. So I've added these two values. If I make them both 0, it's black. If I increase one, either one is going to get brighter. And if I do 0.5 on both, this is going to equal 1 because it's 0.5 times 2. And if I compare this to a value of 1, it's going to look the same because they're both a value of 1. There's a whole list of operations here. Most of them, like add, subtract, multiply, whatever, but there's probably some you don't know. We're not going to use most of these, but one important one is sine. So we have sines and cosines where as you increase this, it's going to go from black to white to black to white. So this is a good way to kind of have repetition where we're using this sine wave, right? Where we have bright areas repeating and then dark areas repeating. If we have a single number, you might wonder, can we have multiple numbers? The answer is yes. A simple way to think about this is you can actually bring in a color. So instead of value, you have a node called RGB. That's red, green, blue. You view it and basically it, represents the color of whatever you pick here. Pretty simple. Now the reason I call this multiple numbers is you can see it says red, green, blue. This is actually 3 numbers where if I open this, you can see if we go to RGB, there's literally 3 numbers. So if I set the first number to 1, it's going to be red. If I set the second number to 1, it's going to be red plus green, which is kind of this yellowish. And if I have 1 on all, it's going to be white. And if all these are 0, it's going to be black. So these are 3 numbers representing a color. And really what this is it's something called a vector. A vector is basically a list of numbers that, generally has more than 1. In this case, we have an X, Y, Z or a red, green, blue. Instead of a color, we can also just use a straight up vector. These are basically the same thing, but we just think about them a bit differently. Where again, we have red, green, blue, essentially. If I set X to 1, it's red. If I set Y to 1, it's kind of the yellowish. It's the exact same thing. The difference with this node versus the RGB node is you're going to see that this one actually has connections, which means we can vary what's going on. So for example, in the X component, and you can just drag and write something in, I'm going to have the sign of some value. Okay, so now it's going black to red to black to red. And then let's also do one on the Z. So this is going to be blue. And for the value, I can connect the same number to both of these. So this is our most complicated network yet. The way you want to read this is we have a number that is going through 2 sine functions, and one's going to X and one is going to Z, where you can see it's going black to purple, or kind of the magenta. And you might wonder if these are the same. Why don't I just use a single one of these? That is correct. Going to give the same thing. But the reason we might want to separate these is I want to do different things for red and blue. For example, I can add an offset of, let's say, pi here. So now these sine waves, instead of being like in sync, one is like this, and then the other is perfectly out of sync. In fact, it's actually a cosine wave, where now you can see there's more going on. It's going red to blue to red to blue. And by the way, just a tip, if you don't want to keyframe or animate this, you can click this, type hashtag, which basically means I'm going to make an expression, type in frame, and this is literally going to give the frame number. So I'm on frame 25, which means that this is going to be 25, and as I go down, I'm going to do that. Additionally, I can take this and divide it by something like 10. This is going to take the frame number, it's going to divide it by 10, which means it's going to be smaller, which means it's going to move slower, and now we have the same thing, but it's a slow evolution. Remember, I can apply this material to any object, so this has the same material, and now they are both flashing. Just like we can add numbers or values together, so too can we add vectors. So here I have 2 vectors. This is a vector math node, so instead of a math node, there's something called the vector math node. Each one of these can inherit a custom vector, or if you don't need this control, you can just type it in right here. So red plus blue is equal to purple, or I can add even more red, and it's going to be brighter, maybe some green. If all of these are -1, which does represent a negative thing, but it's going to show up as black, and then I add a value of 2, it's going to be white, because -1 on each component plus 2 on each component is equal to 1 on each component. These are a bit more confusing. You might not know them, but some of them are familiar. Add, subtract, multiply, divide. If I have 0 times any vector and we multiply it, nothing's going to change because it's always going to equal 0. But if I set this equal to 1, basically only the second vector is going to represent because we multiplied by 1, which means it doesn't change. Now, so far, we've outputted a vector or a single number to this whole surface, right? Anything we do is reflected on the entire surface, but what if I want one area to be black, one area to be white, and maybe a gradient going between them? Well, this is where we introduce coordinates. And since we are together learning about Blender shader nodes, you need to know about the best place to learn things online, which of course is Skillshare. Skillshare is the best place to learn things online, whether that be digital skills, life skills, it's got it all. There's all kinds of categories. So you could do film and video, that seems relevant to us as like Blender people, graphic design even more so, animation, and we could even get specific. Let's do Blender 3D, and you can see all kinds of courses, some of which are very like recent, like the Dune stuff, all kinds of people that actually seem quite familiar. We also have learning paths. What these are is they're basically like a curated sequence of a bunch of like courses, one after another that tied together, so you go from 0 to hero. So recently I've been making a weird like website where you can like type things in, and it's a fun text editor with sound and all this, fully dependent on HTML, which I don't know much of. So let's say we type in HTML. Here you have HTML and CSS for beginners, code your first website. It's basically the idea of how do you make a web page without really knowing what that is, made by Rich Armstrong. This is a course that is super helpful if you don't know the idea of tagging, what are divs, and all of these things. It is summertime. I don't know if you've looked outside. What that means is that you have a lot of time to learn something online and finally do that thing you said you'd do, whether that's like making a website or learn 3D animation or whatever it might be. So you guys can check out Skillshare, and if you use my link in the description, the first 500 people to do so will get a 1-month free trial of Skillshare, which is plenty of time to watch a lot of stuff. There is a coordinates node. It's called texture coordinates, and you're going to see all these things that look confusing: generated, normal, UV, object, camera, windowed coordinates, which is interesting because it actually depends on where it is on your screen. And if we use one of these simple coordinate systems like the UV coordinates, you're going to see that we basically have a graph going on here where in the bottom left corner it's completely black, so this is a value of 0 down here. And then as we progress this way, you can see it gets redder and redder and redder. This actually represents the x-axis, which is also represented by red, and this means we're increasing on x until we get an s equal to 1. Conversely, if we go up this dimension, right, it gets greener and greener and greener, just like the y-axis is green, until we get a value of 1. And then if we go diagonal, we're increasing both x and y at the same kind of rate. So up here, we expect a vector of 1, 1. This is a 2-dimensional vector, but actually it is a 3-dimensional vector in a way, because we have a z-coordinate that is suppressed. So instead of 1, 1, this is 1 for the x, 1 for the y, and then 0 for the z is what's actually going on here. Which means if I take these UV coordinates, and this is a vector, right, you can see this kind of purple output, I can do a vector math, right, so nothing changes. But if I add a bit of z component, you can see it's getting a bit more blue because we can add a kind of tertiary component, the z component. You're going to notice that this one is called UV, and that is no accident. We can actually go to our UV editor, and whatever we do with these UVs translates, right? So this is kind of the bottom left black corner, and if we shift it, you can see now the kind of center point is in the middle because this is the area on the bottom left. Like I said, there's an x increasing and there is a y increasing. Can we look at one at a time? Yes, because if we can take a vector and write it as a combination of x, y, z, right? So too can we separate a vector. So I'm going to separate x, y, z, and now instead of this 2-dimensional, actually 3-dimensional coordinate system, I can see the x component increasing. Remember, black means 0, so this is an x component of 0, and as we increase, we get brighter equal to 1. Same thing with the y-axis, and you bet that we can do all kinds of operations like addition, right? So now you can see that has more of a visual effect, or I can take x and y and include both of them where we now add their components. This is going to be equal to 0 because x is 0 and y is 0, we add them as equal to 0, and then up here, you can expect a value equal to 2 because x is equal to 1 and y is equal to 1, and we added them. Let's multiply them together. Now we get a more interesting result where we have x times y, and you can almost see this kind of like, I forget the name, there's a name for this curve. I don't know if it's hyperbola or whatever, but it's no coincidence that you can actually see this curve, which is kind of the equation you're used to graphing. In fact, I can take this and look at where this value is equal to something, so I can use the compare function. So this is a new one. You can see there's actually 3 inputs. What we do is we compare input 1 to input 2, and we use this epsilon value to say where are they almost equal to each other, right? So as I decrease this, you're going to see it kind of gets thinner because our threshold for where these are equal are kind of getting slimmer. So let's see where x times y is equal to 0.5 with an epsilon of something very tiny. Well, what you can see is that this generates a curve that I can actually sweep, right? This is literally the equation. Let's do 0.25. What I'm doing is I'm checking where x times y is equal to 0.25 with a bit of a plus or minus with this epsilon. You can make it really tiny so it almost generates the exact curve. And if you rearrange this equation, we have y is equal to 0.25 divided by x, which you might recognize as the equation for whatever this thing's called. Can we graph other things? We sure can. Let's actually take x and take the sine wave of it. And what I'm going to do is I'm going to compare where the sine of x is nearly equal to y, okay? And you can see it kind of gives this gentle curve, but we don't actually see our sine wave, and this is because, again, x is going from 0 to 1, so we can only go from sine of 0 to sine of 1. And remember, a sine wave has a period of 2 pi. It takes 2 pi of input to get from, one place to the other, which means if I take our x component now and multiply it, you can actually just write 2 times the I pi, and we get a kind of a sine wave. You can see we have the top part, but why do we not see the bottom part here? Let's think about it. Well, remember, our y goes from 0 to 1, whereas sine can get negative, which means it's down here, which means we can't see it. If I actually take this sine wave, and let's say we take kind of the inverse, I'm going to multiply by -1, now we get the other section because we flipped it around. Additionally, I can take something like a absolute value, and now we get this hump because the sine wave was like this. This is the negative component, and I'm saying make it positive. But what if I wanted to capture the full sine wave, also this negative? Well, in that case, I need to remap our y 0 to 1 to something like, it should be able to go down here, -1 to 1, because that is the codomain of the sine function. Well, there's actually a node for that. It's called map range. The range is basically how far does this go? Again, y goes 0 to 1, but I want to increase the range to go from -1 to 1. And what you can do is we said we're looking at the y component. We're going from 0 to 1, and I want to remap that to -1 to 1, and now we get our sine wave where I can multiply and get, let me make this a bit thicker so we can see, where we can get kind of multiple periods of the sine wave. And one thing to note about what we're doing here is it has infinite resolution. No matter how much I zoom in, there won't be pixelation because this is a mathematically perfect equation. By the way, remember, all of this is ultimately dependent on our UV coordinates, which means I can basically stretch it, because if I stretch it, our UV coordinates don't change, so it's forced to still use this whole area, so it stretches, but I can do something more complicated, like let's say I do a torus, it inherits this material. Well, now you can see it's doing something very weird, and it's not making a sine wave from like the top perspective because our torus has its own UV map. So if I go to the UV editor, you can see our torus has this map, and I can move it around. So too can I take this UV coordinate and sample different sections of this. By the way, if you're noticing that there's this very weird kind of like section over here, that's because our map range strictly goes between -1 and 1 without any kind of leeway for going above 1, right? Like when we go to 1.1, 2, it doesn't like that, and same with the negative. You can change that by hitting this clamp where we're no longer clamping, we're no longer saying this is a limit with this thing. By the way, clamping you're going to see is an option in all these math nodes. It's basically saying if we have a negative value, so let's say we have our timeline, here is 0, here is 1, and here is -1, we're saying this whole section, all the negative, should just become 0 when we clamp. And you can see that over here, it kind of becomes a flat line. Now, what if we want to make a more complicated shape? Like let's say we want to make a circle. Well, if we want to make a circle, we kind of need to know the equation for that. Well, a circle is basically the set of points that are equidistant from the center. So if this is the center, you're going to see every point in the circle is the same distance of the radius away from that. If you'll remember, the radius, which is basically a distance, is calculated by the Pythagorean theorem. X squared plus y squared is equal to kind of like z squared, but we take a square root, and now this is a distance basically. So if I want to calculate the circle at 0.5, so we go halfway on the x, halfway on the y, what I need to do is kind of do this calculation. So I'm going to take the UV coordinates and I'm going to separate them. So we have x and y, and I want to know kind of the distance from this center, which we can calculate by subtracting 0.5. So you can see now it's kind of moved to the center. By the way, this is going to be negative values, which you can correct for by just taking a absolute value. Ultimately doesn't matter because we're going to square it. So we have x squared compared to 0.5. So let's take a power of 2. So this is squared, and then we're going to take y squared, and we are going to add these together. I'm just doing the equation, and now you can see we kind of have the outline of a circle. And finally, we are going to take a square root, and we want to check where this is like equal to 1, for example, and we know how to do that already. I can compare this kind of output to the number, let's say 0.5, with a epsilon that is very tiny, 0.25, and now we have the equation for a circle we can pick a different radius for. But notice, before we did our compare, we had something called a field. A field is basically saying each point on the surface has a different like value we're evaluating at every shading point, where the center is quite black because the distance from the center to the shading point is very tiny, and then as we go further away, it gets bigger, which means we could do all kinds of things with this. We don't need to say where this is less than or greater than or equal to something. I can actually take this, and let's get weird. I can take the sine wave of this, and we don't see it quite yet because again, we need more periodicity. So I'm going to multiply this by a bigger number, and now you can see we actually have something more complicated. So originally, we basically had a function that tells us the distance from the center, and along this, I'm calculating a sine wave. So now if I take this and do some kind of comparison, so I'm going to compare here to like 0.25, you can see we get something more complicated. Let me lower this epsilon by like that. You can also kind of offset over time. So we changed our periodicity. I can also add to change the phase, and this is something we can do over time. So I'm going to write hash frame. You're not going to see it because it moves quite quickly. So I'm going to do the frame number divided by 10, just like before, and now you can see these kind of ring. I can also take our distance function, which by the way, if you want to put all this in one like category, you can either take this and hit Shift T to put it in a frame or a panel, P for panel, or even better, take it, Control G, and now it's in something called a group. So I'm just going to make this only have a single output instead of like 1, 2 outputs. So this is Shift click, right drag. I'm going to take this, Control G, this is a node group, and I'm going to call this distance. So this is our distance evaluator, and then I'm running all kinds of math to do something like that. But I can take this distance field and do other things. So let's do a map range. So again, this distance basically goes from 0, and then it increases to 1 to 2, and it keeps going. Well, I can take this range and invert it, 0 to 1 to 1 to 0, or I guess I want to make this tinier. Now we kind of have this soft circle because we're limiting it from 1 to 0, and I can take our kind of sonar thing and then multiply it by this, and you can see now we have the same thing, but it's kind of limited. And if we think of this as a sonar, it should probably be green. So I can combine X, Y, Z. Remember, this is a vector with 3 numbers. If I want my sonar to be green, we need to increase the Y, or the green component. So I'm going to put this here. I'm going to view it. And now we have a green sonar, where we can increase the epsilon to kind of get this more visible sonar, or multiply the periodicity to get a more dense sonar. By the way, if you don't want this shrinking to the middle, but instead expanding outwards, all I need to do is take this and invert it. So you can take the frame number, take the negative frame number, and now it's going outward. Or simply, you can just take this output and multiply it by -1. Okay, so we have our sonar, but we need something to be detected by the sonar. So let's say we have kind of like a target over here. So in other words, we have a circle that should be showing up on the sonar. Well, remember, we actually already know how to do this. This is basically the circle. I can take our UV coordinate, calculate the distance, but now I don't want the distance from the center. I want the distance from something like over here. Well, one way to do that is I can either take our UV coordinate and kind of offset them, which also kind of does the right thing. Say I don't want to mess with my UV coordinates, I just want to mess with our distance. Well, remember, we're calculating the distance from the center, so hit tab to go inside of here. We're calculating the distance from x value 0.5 to y value 0.5. What if I want one distance function to calculate from the center and another from here? So you want to duplicate, and these do different things. Well, the issue is, so these are the same right now. The issue is if I change one of them, it changes the other. These are the same now. So I want these to basically be independent, and I want to control the x and y without going in here. Well, if I go in here and take the x component and do this, so I'm adding it to the group input, these are now input. I can change the x and y, where you can see we have numbers that are exposed, and these will give us different results, because one is looking for the center from like 0.2 to 0.5. The other one is using 0.5 to 0.5. So by the way, if you don't want these called value, but you actually want to remember what they are, go into the node, hit N for the panel, and you're going to see all these options where we can actually take this value, rename it to x, take this, rename it to y. So you can see that updated here. And then for the output, we can call it distance. And then for the coordinates, we can call it coordinates instead of vector. So now we know exactly what to do with this. Okay, so we have our sonar, but we also want to target. We know how to do this. I use the distance. I use the map range from before. And now we have kind of this like circle that I can move. And if I want to take, before it becomes green, but if I want to take our sonar map and then include or add this, how do I combine them? Well, I just said it. We combine their influence, right? So I can take this whole thing and I can add it to our circle. So now both are included. In fact, I can kind of make this sharper if I don't want it to be the soft circle by saying, so here we have our distance map that was inverted. I want to make it a sharp circle. So I can just say, take this field and tell me where it's greater than or less than some numbers. If I use greater than, now you can see we have this, and we include this into our green, and now we have a sonar. You're going to notice, by the way, that this overlapping section's a bit brighter. If you want that good, if you don't, that's an issue. The reason it's happening is we have contribution from this where it's equal to 1, and also this where it's equal to 1, which means where they overlap, it equal to 2. We don't want that. Well, similarly to how we clamp the blacks, I can also clamp the white values. So we can't go below 0 or above 1. Another way to do it is instead of adding, I can say we want to add them, but only keep the bigger of the two and don't like literally just add them to become 2. Well, if we're keeping the bigger of the two, that is called a maximum. This is another way to do it. Another way to do it is a minimum, which will give us kind of the inverse. You can think of that as a intersection. I want this to also fade our dot. So all I need to do is kind of change the order of operations where I have this output and this output. I'm taking the maximum, so it combines them. And then for this, I'm going to multiply by our like soft mask. So now we get something like this, a little hard to tell, but if I move it towards the edge, you can see it kind of gets fainter, and we make that green. Cool thing about this, by the way, is we can just repeat this. So remember, we have our distance, which we can modify for each one. So maybe this one will be a bit to the left. We put it through these same nodes. By the way, if you just want to keep it simple, this, which goes from our distance to a sharp circle, can also be a node group, Control G. So I'm going to call the circle maker. Here, I can have our distance go into a circle maker, but it's using a different distance input from the other one. Just like before, we have our sine wave, we have our circle, and we took the maximum between the two. I want to also include our other circle, so I can take this and then take another maximum, right? By the way, Alt-S to kind of shift these, although in this case it doesn't matter. And now we have both circles that we multiplied by our soft map that we make green. So this is our sonar, and you can also have these targets move over time by saying we take the x component. So let's actually do this explicitly. I can take the x component that was 0.33, and then we can add or subtract some value over time so that it's moving. I'm just going to use a driver, hash frame divided by 10, which will go a bit too fast, so I'm going to divide by 100, and now it's slowly moving across the screen. We can make it even slower. Whereas this, I can also write hash frame divided by 100 here, but this one I also add 0.52, so you can make your expression more wild. But a sonar usually has this kind of like rotating thing that basically like scans as it updates. It rotates. Well, to do that, I basically need a new function that takes our coordinate system and from the center kind of gives us the angle. Well, class, you'll recognize this as the polar coordinates, where instead of Cartesian coordinates, right, we go from x going from 0 to 1 and y going to 0 to 1, and a point here is basically its x component and then its y component. A polar coordinate system is instead given by, so instead of like x and y, it's given by an angle and a radius, right? So this point right here is basically defined by the angle, theta, from the x-axis, and then the radius from the center. Or a point like this can be an even larger angle with a smaller radius. So we're just kind of converting. Well, we already know how to calculate radius from the center. That's just our distance function. I'm going to put that here. We're calculating the distance from the center, 0.5. This is our radius, which I can just rename to radius, but we also need to calculate the angle of every point. Well, this is kind of a special trick where, let's say we have an angle equal equal to theta, this angle is still defined by x and y, right? So we go some component. So let's say we have this, we have some component on the x and some component from the y. And remember, we want to calculate this angle over here. And if you remember SOHCAHTOA, sine, cosine, tangent, you're going to see that this is the opposite, right? The opposite over the adjacent, right? So tangent, let's write this down. Tangent of theta is equal to opposite, which in this case is going to be the y component. So opposite divided by adjacent, which is the x component, which means if I take a inverse tangent, right, on both sides, we're going to find that theta is equal to the inverse tangent. So inverse tangent of y divided by x. In other words, we have a complicated equation for the angle. If I want y divided by x, we have our UV coordinates, which are two-dimensional, actually 3. I'm going to connect this here so we get the x and the y component. And instead of doing this division and inverse tangent, there's already a function for us. It's called arctan2. Tan2 does the division for you and some other thing where I can say this is y divided by x. And now this is going to give an angle. It's a little hard to tell, but it's going to give an angle from the center, which is actually over here because we didn't shift it yet. So remember, our UV coordinates are equal to 0, 0 down here. We just didn't shift them, but this gives an angle where I can do a greater than to see. It gives an angle that sweeps. But if I want to calculate the angle from the middle, all I want to do is take our UV coordinates and shift them this way, which means, like we know, you can take the vector math and do a subtraction or adding a negative. So I'll subtract by 0.5, right? You might think that you want to add 0.5 to get here, but it's actually the inverse because if this is equal to 0.5, when we subtract 0.5, it becomes 0. You're going to see it looks a bit weird. The way this is working, by the way, is you can see it sweeps like this, but then it kind of stops. And it stops at not just a random number, but a very specific number. This number you might recognize as pi, but you can also go the other way, right? So the thing is, this output a value 0 to pi for an angle, but then it's 0 to negative pi over here. But what if I want it to go from 0 to 2 pi, like normally? Well, this section's fine. This is the section I want to invert. Well, if I want to invert the bottom section, all I need to do is isolate it and then multiply by -1. Well, how do I isolate the section? This is where the y component, the y, the height, the vertical, is less than 0.5, right? The bottom section. In other words, I can take this y component that we had from before. I'm going to see where it is less than. Oh no, we already did our shift here. Remember, we did this. So what I can do is either do it with a separate UV coordinate, or let's just do it with a separate UV coordinate to keep it simple. So again, I'm going to separate my UV coordinates. I want to know where our y component is less than 0.5, right? This is the bottom section. For this, I want to take the arctangent and multiply by -1. So the issue here is if I take this and then like multiply by this and then like multiply by -1, it all kind of gets a little weird. So what I want to do is I want to say for this top section, do nothing, and for the bottom section, multiply by -1. Well, here is another important node. It's called the mix node. What the mix node does is allows you to have two numbers like 0 and 1, and then you can switch in between them with this factor. So when this is equal to 1, it's going to use the b, and when this is equal to 0, it's going to use the a. I can just have arctangent, and then for b, I can take the arctangent and like we said, multiply by -1. So something like that. So we have arctangent, and then this multiply by -1, which you can see kind of inverts it. And the difference between using a and b should be this kind of mask here. So we do this, and now you can see we have, this is actually not exactly what we want, but you can see now we have our full spectrum where if I do a greater than, it's actually going to give something different. It's going to give this pi wedge, kind of like a Pac-Man eating, which is actually pretty interesting. This is because we go from 0 to pi, but then in this section, we're also going 0 to pi. So multiplying by -1 was kind of the right idea, but really what I want is we had this 0 to negative pi. This should be remapped to pi to 2 pi, kind of confusing, but we know how to do this. We have our arctan2, and we know I just want to remap the range from, remember it's going from, you could do it either way. Let's say we're going from pi to, or sorry, negative pi to 0. We go from negative pi to 0, and that should become, so right now it's going 0 to 1. This should become pi to 2 pi, right? I'm just redefining this, and then this is what I want to have as our b component. So now we have 0 to pi, and then for the bottom section, pi to 2 pi, and now we have a full sweep, okay? Very complicated. But kind of the takeaway here is now I can do kind of a compare function where I can say, where is this equal to, let's say, pi, right? Which should be this direction with an epsilon of 0.05. And as I sweep this, it's going to give a circle. By the way, another issue, when we go from 0, it's good. We increase, and then we're at 2 pi, and then it goes away. Why is that? This is because our angle goes from 0 to 2 pi, but then we don't increase, right? And then go to like 3 pi and 4 pi. It just goes from 0 to 2 pi, which means this compare is going to break at a certain section. So if I want to sweep, I somehow need to say go from 0 to 2 pi and then go back to 0 and 2 pi and all this. In other words, the range 0 to 2 pi is totally weirdest to ever, is totally fine. But then as we go from 2 pi to 4 pi, it should again become 0 to pi. Same with 4 pi to 6 pi. Basically, we always need to bring it back. In this case, it would work by just subtracting 2 pi. 2 pi would become 0, 4 pi would become 2 pi, etc. So let's actually just, take a crack at this. So what I can do is I can just, let's actually do it as a value to keep this simple. So here we have a value. I'm going to take the frame number. Remember, frame 0, it's black, and then it gets whiter. We actually start on frame 1, it's white, and then it gets even more white. This is something that should always remap 0 to 2 pi. Let's take this and first of all, divide by 10 so that it grows much slower. And then I want to know when this has exceeded 2 pi. So I can take this and say, when are you greater than, let's say, 2 pi, right? So in the beginning, it's going to be black, and then as we play, eventually it's going to become white. Well, in that case, what I want to do is then remap it to the beginning. And there's a math node for that. It turns out it is called fraction. What fraction does is, let's say we have a timeline that increases from, let's say, 0 to 1 to 2. What it does is it takes each one of these sections that's above 0 to 1, and it remaps it to the beginning. The way it does this, and the reason it's called fraction, is let's say we have a number here, like 1.3. What it does is it basically truncates, it gets rid of this 1, which makes it equal to 0.3, which means it's remapped back here. So too, if we have 2.3, it will just get rid of the integer component and then remap to 0.3, and it does this over and over and over again. This, with the fraction, is going to be kind of blackish and white, and then it repeats, because it keeps going from 0 to 1 over and over again. But if I wanted to go from 0 to 1 to 0 to 2 pi, I just multiply this by 2 pi, connect this here, and let's see what we got. We have our circle, and it goes on forever because we keep going 0 to 2 pi. To make this slower, I'm going to divide by 100. So what I am going to do is I'm going to take this whole nonsense over here and just keep it simple, where I'm going to control G to make this a node group. So now we're a bit cleaner here. By the way, take a node, control H to hide every socket we're not using. This is going to be our angle. Have our angle. Actually, inside of here, I'm going to bring back our compare node. So I want to compare this to, let's say, 0 with an epsilon of something a bit bigger. Okay, actually, we did that wrong. We have our angle, and then we compare to this like changing value with an epsilon of something tiny. I want to take this and add it to our sonar. So remember, we had our sonar, we added a dot, we added another dot, and then we multiplied by our phase. Just like before, we add one more maximum, including our angle. And now we have all of these components that we dampen and we make green. No reason you can't take this and make it blue, right? Using the Z component. In fact, here's a way you can think about it. We can take a vector math, which again is a 3-dimensional thing. You could think of it as a color or a vector. Let's say I pick the color red. I can take this and I can multiply it by this map right here, which is 0 to 1. So I'm going to multiply. By the way, if you put a number inside a vector, so let's say this is equal to 0.1, what it does is it's not 0.100. It makes it equal to 0.1 on X, Y, and Z. It just treats it as a vector where it's the same everywhere. Now we have red, and we can kind of change this nice and dynamically and pick a nice color. I'm going to go for green. And again, everything we have here, beauty of the nodes, completely controllable. So I can bring down the periodicity, and now we have a sparser sonar, denser sonar. Okay, let's move on to a different section. We talked about numbers, vectors, and coordinates, and now let's talk about 3-dimensional things, right? We've been stuck on 2 dimensions. Okay, so for part 2, I'm thinking we change what kind of coordinate system we're using. We're mainly going to talk about normal coordinates, and now our goal is to do more vector map and create more interesting materials like moss or grunge or dirt or whatever. So this time we're going to use not a flat plane, but very intentionally I'm using a mesh with kind of like curvature and different faces. And in the shading workspace, I'm going to apply a new material, and just like we've been doing, I'm going to bring in a coordinate system, specifically normal coordinates. Now, what normal coordinates describe is not like the thing we're used to where we have kind of like an X, a Y, a Z axis, and we know like how far along we are. No, a normal coordinate basically tells us what direction is facing outwards from the mesh. So here it's this direction, here it's this direction. You're going to notice this is actually going to change with the geometry. So as I increase this and maybe give it a bit of rotation, you can see that color is changing because now the direction that is going outward is changing. Additionally, if I shade smooth, it's going to smooth the coordinates, unless of course we don't want that, where we can use this geometry node. Don't worry about it, where we have normal coordinates and true normal, which don't change under shade smooth, but we actually want it to. So why is something like this useful? Well, it's useful to know which direction is outwards, because then we can define more complicated surfaces. So instead of saying, oh, only extract the top section of this, if I wanted something like moss or dirt or whatever that only accumulates on the top, but not on this like overhang over here, this is where normal coordinates come in. So for example, let's say that, again, I want to drape something over the surface. In other words, I want it here, I want it here, I want it here, but I don't want it in this direction because it's facing kind of downward. Well, how do I describe that selection in 3 dimensions? Well, here is a new operation that you might have not heard of. It is called the dot product in vector math, and what it tells us is something about the angle. In particular, if I have a vector going upward, so again, a vector is a 3-dimensional quantity. In this case, it is 0 on the X, 0 on the Y, and 1 on the Z. In other words, this is the direction that's going straight up. Let's say I have this vector and then also the surface normal. You're going to see in this case, the angle between them is actually quite tiny, which means they're almost aligned. Whereas somewhere like here, we have our upwards Z vector and we have a surface normal, and this angle is huge. In other words, if we can extract this angle, we know what is kind of facing upwards, and this is what dot product does. So I'm going to plug in the normals, and for the second vector I'm comparing, I'm going to use the Z up direction. When I view this, you're going to see it gives this kind of interesting output that indeed kind of isolates the top of the mesh, but more particularly, it kind of gets rid of these overhangs, and this is very sensitive to mesh deformation. So you can see, let me actually rotate it the other way, you can see we're actually starting to re-expose sections of it as it's like pointing upwards. Now, the dot product doesn't actually give you an angle. What it does is it compares the two vectors and then gives you a value between -1 and 1, very similar to sine and cosine. It turns out, though, that you can take this and convert it into an angle using this special formula, the dot product of two vectors. The first one's going to be called V, the second one's going to be called W, because I say so. This is basically equal to something related to the angle, but really it is the cosine of the angle, which tells us we're going to need to take a inverse cosine to extract this. And then I believe it also cares about the magnitude of the vectors, like how big or long are they. So it might not exactly be this, but I think it's the magnitude of E times the magnitude of W. But if we can make sure that these are both equal to 1, then we don't actually care about that. And to make sure that our vectors are of distance 1, that's also called normalize. What we can do, and they actually are already, but you can bring in a vector math, and there's an operation for this. It's called normalize. What it does is it makes sure that if you have a vector pointing in this direction, it maintains that vector, but it makes sure that it has a magnitude of 1. So this is a vector, this is the normalized vector. Just make sure it has a length 1. But as you can see, 0, 0, 1 obviously has a height of 1 because it's only on the z-axis. So if we take this and then take a inverse cosine, which is going to give us something kind of similar, it's called arc cosine, but this is going to give us the angle. This is exactly going to be black wherever that this is kind of pointing directly upward, which we can actually isolate just like that. So this is a good way to find where there's water because it always kind of goes level to a thing. But that's what you got. Now, it turns out we don't actually care about this because we can still use this -1 to define something, but let's kind of stick with that. So let's say that we have kind of like moss on the top and not moss on the bottom. Remember, we do have this kind of like mix node we've been talking about where we can make this the factor. So I can make one of these 1, the other 1.5, and it will basically choose as we, let me like decrease this value, it will basically choose what gets like what value depending on what is black and what is white. But it turns out there's not just a mix node, but there's a mixed color, which works exactly the same, right? So I can have one of these be red, one of these be blue, and now you can see we're kind of shifting between them, where in between we have this purple, because this is not exactly black or white, there's some gray in between, just like real life. But we could get rid of that if I say where's this greater than, let's say, 0.5, and now we have kind of like a sharp color if you want that. And like I said, colors and vectors basically the same thing. They're a 3-dimensional vector, which means if we have a mixed color, so too can we use a mixed vector, where let's say one is red and one is blue, so I'm just writing it explicitly, and it gives us the same thing, right? I want this to be grass or moss, really, so it should be kind of like a dark green up here, and then on the bottom it can be kind of like a dirt color, so kind of like a brown. And this is kind of like our basic moss setup that is responsive to the environment. In fact, if I add something with harsher edges, you can see it's only on the top face, but as I bevel, it will kind of fade off as the vector aligns less and less with the z up. Additionally, we can get fancy, and we'll come back to the moss, where instead of having this kind of like up direction, which by the way, you can totally change. So we can say what is facing the x direction, and now it's pointing this way, or you can do that plus y. Instead of something like that, we can use the dot product to create something interesting, where let's say that we have a camera that is facing our geometry. So I'm just going to camera to view to face our geo. From the perspective of this camera, I want to isolate the outline, or roughly the outline of this object, which is not information we actually get inherently without freestyle or something like this. So how do we do that? Well, in a case like this, we know something is vaguely on the outline if it is facing away from us. So this part of the sphere is facing this way, whereas the camera is kind of facing this way to the shading points. In other words, these two basically make a right angle, and they're not facing each other at all. On the other hand, if we have a surface point like this one right here that we're facing exactly, a little hard to see with the 3-dimensional, but these two vectors basically align. They're kind of inverses. But in a case like this, we know what is and isn't facing us. Well, how do we get this vector from the camera to the surface? Well, there is kind of a node for this, but let's do it explicitly. The way we get one vector from here to here is, first of all, we need to know the position of the camera, and second of all, we need to know the position of the surface point. For the camera, I'm going to do this explicitly for now, so I'm going to combine x, y, z. And how do we know the position of the camera? Well, it is written right here, okay? So I can copy this x value, paste it in here. Same thing with the y component, and then finally the z component. So this vector basically represents where the camera is. It's not going to change no matter what direction we look at it from. And additionally, it's not going to change when we move our camera, because then the location is changing and we haven't updated for that. Now, the second thing we needed is the shading point where we're looking on the surface, right? So we need the position of points on the surface. It turns out we don't have that in our coordinates, although it is in a way a coordinate system. You have to use that geometry node I was just talking about, where we have all kinds of things like position that tells us the position of this, which will change, right, depending on where the vertex positions are. And to get the vector from the camera to the position, all we have to do is subtract the two. The reason for this is if we have a world origin where this is 0, 0, 0, the position represents the vector to get to the shading point, so this is position. The camera vector that we wrote out explicitly, so this is c, goes from the origin to the camera. And if we take the position and subtract this camera, in other words, we're going negative, so we go up the position and then this way for the camera, it's a little out of sight. Well, this minus this is basically going to give us this direction, which is parallel to this one. So in other words, what I want to do is I want to take the position, we are going to then subtract away this camera vector. So this is basically going to give us the direction facing this. But remember, for the dot product, we want to always normalize because that will make the equation nicer. And now for each point on the shading surface, we know what direction the camera is facing to get there. And we also know the normal of the surface. So let's actually take the dot product. Let's compare how close these are to each other. So I'm going to use a dot product right here, connect these, and let's see what that gives us. Well, it gives us basically something that is facing the camera. Okay, so it's a little hard to tell, but the outline of this is pretty much black. We can make that more visible by, let's say, this is a thing between -1 and 1. So let's see where this is greater than some number. And you can see we've essentially extracted out the outline, right? It turns out that there is a name for this. This is called Fresnel, which is basically the angle of where we're looking from compared to the surface normal. So here's what Fresnel looks like. So it looks something like this. You can see it's dependent on the angle. So this is a custom Fresnel node where, just like before, we can use this as a mixing to kind of blend dirt and moss together if you wanted to. Well, you're seeing that this is working, but it's kind of very boring and there's a lot of fading going on over here, right? There's no explicit moss and then no moss. And we basically want to take this black and white and kind of compress them, increase the contrast. Well, here's a super useful node to kind of do this visually. So we can take a color ramp node. What this does is it takes a input and one of them is going to be black, one of them is going to be white. And you're going to see as I shift this, it basically kind of recolors our thing. We can actually invert this this if we take both handles and flip them. And most importantly for us is we can take these two and bring them very close together to get kind of like a harsher fall off. Additionally, you can kind of use this as a fancy mix node where the white can be matched to kind of this dark green that we had before, and the black can be kind of like a dirt color. And just so you know, there's a lot of ways to do this. So let me just add RGB curves. There's a lot of ways to define this. Only kind of prerequisite is it's got to go from 0 to 1. That's just what RGB curves like. So I'm going to take map range. We're going to go from -1 to 1 to 0 to 1, right? We remap the range. I'm going to connect this to the color. So you're going to see we get something like that, not much different than what we had before. But now we can kind of sculpt out the look of this and get more custom kind of repetition kinds of things. Just like we could have done before and we did with the sonar, like you can take a sine and do kind of like fancy things along this. So let me multiply for a kind of more frequency thing. Okay, let's get back to our MOS. So we have this and we know how to isolate it thanks to the dot product, but it's kind of very harsh, right? There's no kind of like noise or any kind of organicness to that. And the only way we could do this is if we modeled it ourselves. So we have some up, we have some down, and it creates kind of this distorted thing, which I want. But what if I don't want to model and I just want that detail in the material? Well, this is where noises come in. So if you hit Shift A to add a node, you're going to notice that there's this whole section called texture where we have noise texture, magic texture, all of these. You click one, and basically what it shows you is a pattern that are dictated by different rules that have this kind of organic look to them. So we have noise texture. You kind of learn what these are about. Here's a wave texture. Wave just means repeat, just like we did with the sine wave. And just like we use this as a factor for our mixing, so too can we use the noise texture, which will now kind of fade between these. Note that the noise texture has this socket right here, this vector socket, which means it relies on a coordinate system just like everything else does. By default, it uses something called generated coordinates. We haven't talked about that, but we have talked about UV coordinates, which are of course dependent on the UVs of our mesh. Either way, we're for now going to use this default generated coordinate system. Just for your information, we know normal represents the direction out of the surface. We know UV is the UV texture. What generated coordinates do is they basically take our mesh and make a bounding box. They make the tiniest possible box that kind of, well, let me do this in 3 dimensions. They make the tiniest possible box that contains this mesh. And then for this cube, not a grid, but a cube, it imposes a X direction, just like our UV. It imposes a Y direction, but it also imposes a Z direction. So all of these are 3-dimensional, but this one's really 3-dimensional, right? It cares about our X, Y, and Z, which of course we can visualize by separating out this vector. So here is the X going from left to right along the X axis. You can see that here. Here is the Y that goes this way. And then finally we have the Z that goes vertically. Either way, I can take our dot product and kind of add influence from this by just multiplying them together. So some sections get multiplied by a number close to 0, so they get darker. Let's do it like this. And now we have what we had before, but with a bit of kind of detail. So now when we view this, our MOS looks a tiny bit better. Again, we can kind of change the color ramp here, but we still have kind of this super weird look where this brown is a single color and this green is essentially a single color and there's no kind of detail going on here. But remember, our noise texture has this black and white going everywhere, which means we can incorporate that not only into our mask of where there's MOS, but also into the color of the MOS. And this is where we get into color math. So remember, we have value math. A value is just a number, and you can take 2 of these and multiply, add whatever. And then with vectors, we have vector math. In the color world, you could also use vector math like we talked about, but in the color world, we use mixed color, which I showed you. There's all these operations, which you might be used to from Photoshop. This is all like image editing, Photoshop-y type thing. Some of these make a lot of sense, right? We know what multiply means. It's just multiply these 2 color vectors. Add means add their components, but there's all kinds of weird ones. What I am going to do is in this mixed color, for one of them, I'm going to use our kind of green-brown thing. And right now, just like our normal mix, you can choose between selection A and selection B. So selection B can be red, and we can go between them. What I want to do is instead of saying use one or the other and average them with mixing, I want to say explicitly multiply. So when we multiply this, and this factor now represents how strong the multiplication is. If I use 1, it's really just taking this and multiplying it by red. What that is going to give us is just the kind of darkish, noisy red. Let's think about why that is. Well, we had all this color that kind of takes up the full color spectrum of our 3-dimensional vector space. We'll call it red, green, blue. But when we multiplied it by red, we essentially multiplied it by the vector 1 for red, 0 for green, 0 for blue. We multiply these, we get the red, but then both of these over here are basically canceled out because green is multiplied by 0 and so is blue. So we don't want to do that. We want to multiply in a way that doesn't isolate them. And specifically, we want to use this noise texture. So let's just drag this here. And you can see we now took what we had and we multiplied it with the noise texture, which we can make softer or harder. Our noise texture, you might have noticed, has all these numbers: scale, detail, roughness, whatever. As kind of like a rule, you can think of scale as basically kind of how densely packed is this pattern. So while scale increases, you can see like the parts kind of get smaller. So it's the inverse of what you think. Think of it as density. Let me bring that back down. Detail is basically how detailed, I guess, is this. So this is before and after, it just adds a bit more. Roughness is basically kind of how spread out is this pattern. And by the way, all of this is easier to see if we use a color ramp, not a mixed color, but a color ramp. So now if I increase the detail, you can really see it increasing the detail, and you can really see it increasing the roughness. And if I now substitute out all our like noises with this new high contrast detailed noise, you're going to see we get what we got before, but with more detail. So I'm going to increase the roughness just so it's a bit more distributed. And I'm going to make the black less intense by bringing these kind of further apart. So something like that. It's actually looking quite similar to a Minecraft block. because this is a way to kind of make that material. And ultimately, all of this is dependent on our nodes that we could change at any time. Remember, dot product tells us what direction we're kind of comparing to. So if I make this X, now we have grass that grows sideways, which is pretty cool in its own right. Let's do the Y component. Now it's going this way. And while we have this material totally procedural, so let's actually apply it to a different object and make kind of like a Minecrafty block. So we use a cube, we apply this material, and now we get something like this. Now remember, the reason that this is only on the top face is this is the only one that even remotely faces up. All of them are basically perpendicular at best. But the rest of it totally applies, right? We had our high contrast noise texture and everything kind of maps the way we want it to. If you want it to bleed off the edges, a quick way to do that is we just add a bit of a bevel, and now it kind of bleeds a bit further down because our surface normals are aligned and then a little less aligned and then barely aligned and then not at all. And you could get fancy where you can model, as you go. You can see it kind of updates where the dirt should and shouldn't be. I mean, look, I can inset this and then maybe extrude a block over here that knows it should have grass, and it does a bit of a fall off. By the way, the last thing I'll say here before we wrap up this section is you might have noticed that this noise, basically this black runge, as we kind of stretch it out this way, it kind of stretches out our texture, right? You can kind of tell it's like being stretched this way. I can make it even more extreme, and now look at that, okay? So one kind of issue with the generated coordinate system is, remember, the way generated coordinates work is they create a bounding box for our mesh in 3 dimensions, but if one of these axes is super long, like this y-axis, our bounding box, which always goes from 0 to 1 on each axis, has y go from 0 to 1 over a very big distance, which creates that stretching. One easy solution to this is, like generated coordinates, there's something called object coordinates. They're actually very similar, although instead of using a bounding box, all it really cares about is kind of the origin of our mesh and then how far away each point is, which means we can substitute this in as object coordinates and view it, and now we don't have any stretching no matter how we modify the geometry. While object coordinates doesn't care about edit mode, which is quite nice, so you can see it kind of like changes with our mesh, it does actually care about object transform. So if I scale it this way, you can see it still does our stretching, which we don't want. You can see right here we have this scaling of 8 that is fixed by applying this scale. So Control A, apply scale, and now we're all good. So now we've talked about different coordinate systems and how to make something more complicated. Okay, we're back with part 3. This time we're going to be talking about BSDF, which is actually how you use this thing in Evian cycle. So let's get to it. So what is a BSDF? Well, it kind of stands for like bidirectional surface direction. It doesn't really matter what it means, but what it is it's basically a material. It's basically a shader that responds to lighting. Remember, if I go to the shading workspace and just kind of view our render, and I get rid of this BSDF and just do the kinds of things we've been doing, so let's make this white, it doesn't actually respond to light, because why would it? It's just a value of 1. It doesn't care about the context of the scene. But there's this whole class of nodes called shaders, and most of these are blah, blah, blah BSDF, and these are basically nodes somebody else made that responds to light. There's all kinds. Usually the simplest is considered diffuse BSDF. It's pretty simple. You pick the color, which we know is a 3-dimensional vector. You pick the roughness, which is basically how shiny it is. So let's switch over to cycles. It's kind of subtle, but you'll see the difference as we increase the roughness, right? It doesn't reflect light as much, and it is more green than it was before. But just so we understand what's going on, let's make a BSDF ourselves. So let's make the same kind of thing. So we know RGB lets us pick a 3-dimensional vector. So here we have green, but of course this doesn't respond to lighting. It's kind of like emissive. The shadows don't count. We only care about what's on the surface. Well, to actually shade this, what do we know about lights? If the surface is kind of pointing towards the light source, and of course we're talking about surface normals in this context like we talked about, if it is facing the light, it should be brighter than something like over here that is not facing the light and is kind of obscured, which of course we know how to do as a dot product. So the first thing we need is we are going to execute, we're not going to kill, but we're going to execute a dot product. The first of which, of course, is our normal coordinates. We talked about this. This gives us the vector at every, surface point, every face that tells us which way it is facing. And the other thing we care about is the direction from surface point to the light. We basically calculated this before when we were treating this as a camera, so let's do it again. We care about the position of the shading point, so here we have the position, and second of all, we care about the location of the light. And this is something we subtract one from the other. In this case, I want a vector that points towards the light, so we're actually going to have position be the second socket, and then for the first socket, we care about the position of the light. For now, we are just going to copy it manually, but then I'll show you how we can avoid this. And this is our Z component that again gives us a vector that is position dependent, but as we know, we want to normalize this vector before it goes into the dot product, just so we get good cosine of eta properties, and the length is 1, so I'm going to normalize, and of course you can also normalize your normal coordinates, but they're actually already normalized. It's in the name. So I'm going to take the dot product of these and let's view it, and you can see this gives us pretty much exactly what we want. This face that is not facing the light is in darkness, and the faces that are facing the light, are doing what they're supposed to. When we rotate this object, you're going to see the lighting doesn't update because it actually cares about the position of every vertex. That doesn't technically change when you do an object transform. So if I go to edit mode and now rotate, you're going to see the lighting updates the way you would expect it to, nice and in shadow. Let's say we move our light around. It doesn't do anything except for the shadow, which we can actually get rid of this plane so we can see what's going on here. We want this to actually know where the light is as it's updating, which means we can't just have a static vector. Instead, I can look at this X component and see how it's updating. by right-clicking, we say copy as a new driver, and then in the material for the X component, all you have to do is paste the driver. So what you're going to see is right now it's 2.4, but as I move the light around, there's now something happening. Now it's 1.6. It only updates the X component. So as you expect, we right-click, copy as a new driver. What a driver basically means is it references one piece of data to update another piece of data. And now we've actually done everything we need. Of course, it looks a little janky, but we've done everything we need technically to make a lighting setup. Of course, this only works with a single light. You'd have to add multiple light sources, but it's not too bad. So you can think of this as in full exposure until we darken and use our lighting and everything. So I'm going to mix color. I'm going to multiply our dot product. So full strength, we are going to multiply. And now you can see it's the same thing as before, but it darkens. And technically, you might see here, if you kind of look, it actually has kind of a hot spot that gets kind of weaker radially as it goes outwards. This, of course, makes sense because this whole face does have the same surface normal at every shading point. However, the direction to the light basically changes depending where we are, which means that the dot product effectively changes. So we get that for free. Now, another thing you're going to notice is if I keep this kind of in the same direction, let's just do it upwards, you're going to notice that, yes, it has the hotspot and everything, but the lighting basically doesn't get weaker. I can bring this infinitely high and it's always going to be basically exposed. What we know is as this distance between the surface point or the shading point and the light grows, right? So now it's bigger, it should get dimmer, and that is proportional to an inverse square. So you can think of the light or the strength of the light to be a function of 1 over the distance between the two squared. What that basically means is if we have a height here, it has some strength, but if I now double this, so now it's 2 times as tall, it's not going to get half as weak, it's actually going to get 4 times as weak because we have that inverse square. This is because light basically emits in spheres, the surface area of which is a function of a square. Doesn't really matter. But what does matter is I care about the distance between these. And we've already actually calculated distance. Remember, we had the square root of x squared plus y squared and all this, which is the way to do it. But now we know what's going on, so I'm going to give you a bit of a secret. In the vector math, all along, there is a distance function that does this for you. You give 2 vectors, it will tell you the distance. Sorry for not telling you. So our first input is the position. This is what I care about. And our second input is going to be this updated position of the light, and this will give us the distance. However, you're going to see that we wrote this vector in here, so we can't really bring it over here, like we didn't outsource it. Bit of an oversight, but if you think about it, the distance between these is the same as saying, look at the vector that points from one to another, and then give me the magnitude. How long is that vector? What that means is instead of the distance function, which totally works, I can take this vector that is not normalized. It actually has a length that isn't 1 necessarily, and I now calculate the length of the vector. So these are kind of related ideas. So if I view this, what you're going to see is as I bring the light, it's going to get darker and, vice versa. But this is a inverse square relationship. In other words, it should get dimmer as I go further away, not the opposite. So I'm going to take the reciprocal. You can do that by dividing 1 over. Either way, you're going to see it's pretty bright here, and as I move it away, it gets pretty dim, but it does that in some way like inverse linearly. So we take a power of 2, and now it's an inverse square, and you're going to see the darkening. This actually looks like what you're kind of used to. This basically distance function doesn't account for what faces are facing away from the light. So things can be exposed that aren't supposed to be. As you might expect, all I need is both of these pieces of information, so I multiply them together. And now we don't only have this nice strength of lighting, but also kind of the faces that are obscured. This is what we pipe into our green mixer. And now we have something like this. And you might be thinking, how do I make this light stronger? Because if I increase the power or decrease it, it actually doesn't do anything because we made our own BSDF in a way that doesn't actually look at that data. So if you think about it, all we have to do is take this light intensity or kind of this inverse distance, and we take it and we multiply it by some number. If I multiply it by 10, it's going to be 10 times as strong. Just like before, if you want the actual settings for this, we can take the power and create a driver. So now it's at a value of 1,000. I'm going to paste this into our multiplication. Of course, this is going to be super bright because it's taking values like 1,000. You have to get pretty far away to see what's going on. So because we're wanting this to be like somewhere between 1 and 10, you can take this driver and let's go to edit mode. You can actually do a division or an expression by saying, let's do a scripted expression. So right now it's taking the energy of the light, which it knows what that is. I'm going to take it and divide it by, let's say, 100. So it's still dependent on this, right? You can see it's updating, but it's not as intense. Another way to think about this is let's actually make the power super low. Let's set it equal to 1. And then for this edit driver, we no longer need this expression. It can just be the energy. And this is kind of a more sensible way to do it anyhow, because our numbers are going to be small anyway. So let's try it on a sphere. So let's make that a bit bigger. Now you can see we have a bit of a smoother situation, and you're actually seeing this setting where you can see every single face. And that is, of course, because our normals that are, used to calculate the dot product, those are kind of quantized where we can shade smooth, and now they're no longer quantized. In the worst case scenario, this unlit section is basically black. No light is reaching it, which of course isn't realistic when we have this gray world. It would be realistic if I kind of darken the background, right? Like this is what you'd see in something like space. Let me actually save this bad boy. It is what you would see in space, but our background is gray, so there should be some ambient light. So this is the concept. When you have diffuse, you have directional lighting, which of course we have right here, but you should also have ambient lighting. We just add a bit. And of course, if I'm saying that we are to add a bit, we can do that. So I guess what we can do is after this dot product, I don't know if this is precise, but after it, we multiply and all this, I can just add a tiny bit of a boost. So you can see here we're increasing our ambient lighting. Let's set that to 0.2. And now, yes, there's a bit of a background thing, but we can actually, I don't know, we can see what's going on here. We do have all of this, and it does seem to have lighting and everything we'd expect, but it's still a little hard to see the form of this. It actually looks like a flat circle in this case, which might be accurate with the lighting, but I just want to see a bit of a rim light. And remember, we did make a function that will exactly tell us the outline, or what we call the Fresnel. This time, because I don't want to do it again with the camera and all this, remember how we did it with the dot product? We basically swapped this out for a camera and didn't use inverse square. We are now free, I'm claiming, to use the Fresnel node, okay? We've done it already, it's good enough. And I'm gonna have this like Fresnel outline be brighter on the edges, which it is. So you can either do this additive or as a multiplication. I'm going to do it as a addition. So we have our ambient light, and then further, I'm going to add this Fresnel, which might be a bit intense. We can change it later, but now we can actually see the form of this quite well. You might argue that this Fresnel should also be a function of the dot product. Let me think about this. If we wanted that, what we can do is instead of adding after the fact, we can take this Fresnel and add before the dot product, so it's affected by it. I don't know how I feel about that. It definitely adds something, but for my purposes, I'm not saying this is physically accurate, but for my purposes, I'm going to add it after. And we can play with something called the index of refraction. Basically, you can think of it as the harshness of this situation. There's a technical definition of how much it bends light and all this, and I'm going to make it a little less intense by multiplying our Fresnel by a tiny number, like let's say 0.3. Now, this technically isn't enough logic to do every kind of scenario. So if I have a torus, I shade smooth, you can totally tell it's a torus. However, you're going to notice something weird. If I put this light over here, indeed, this section is in shadow because it's facing away from the light, but let me do this kind of perfectly, the perfect scenario. So this section is lit. You're going to notice that this section is also lit, which if you think about it, doesn't really make sense because the light ray shoots in this direction. It then hits this shading point and makes it a certain brightness. But then if this ray was to continue and hit this shading point, it's already been obstructed, right? We have no information that says you've already intersected the mesh essentially. And this idea I'm describing is actually the idea of shadows, like light intersecting surfaces, not just kind of like this dot product looking thing, but actual shadows. We're going to need to have kind of this collision system that tells us, did we intersect something? Now, this is kind of hard to do by itself because we don't have information about intersection, right? I can start at a point and go towards the direction of the light, but how would I even know if I even intersected at any point? Well, it turns out there's many ways to do this with SDF and something called ray marching, but for the purposes of this tutorial, we're not going to do it because the way I know how to do it is with ray marching or ray tracing, and that takes a while to implement. So for this plane, I'm going to shift click, Control L, link materials. Now, both of these kind of have this situation, and our scene can be properly lit, whereas we go further away, it kind of gets darker. I think our ambient light is definitely a bit strong, so let me make it like 5 times weaker. You could also make it a function of this kind of like inverse square with a strength thing, so you can multiply it like this. And now the Fresnel is definitely there. You can tell that there's a difference, but it does kind of go away at a certain point. I think this is more physically accurate in my mind. So we created a BSDF. Beautiful. It isn't, fully featured like the diffuse BSDF is, right? Diffuse BSDF has shadows, or it works with shadows. It also has roughness, and it has something called normals, which we'll talk about. By default, it actually uses the normal coordinates that you're used to. So if I type in coordinates, use normal, it doesn't change anything. But the moment I modify these coordinates, like I shift it like this, you can see it does lighting stuff. So if we were to affect the normals, it affects kind of the shading. And this isn't surprising because if we take our normal coordinates here in our custom setup and let's do a vector addition, we also kind of get this weird effect. So it turns out if we modify our normals just a little, we can get kind of cool shading effects, but we'll go back to that. Now, instead of this green, let's do something more interesting. Remember, we talked about different kinds of textures, like a noise texture, for example, that has this 3-dimensionality to it. So let's actually use object coordinates to prevent stretching. If you're seeing that this is denser here than on the grid, the density of the noise, we talked about how this doesn't like necessarily change with scaling. So Control A, apply scale, and now it works. I'm going to connect this instead of our green, and now we view it, and we have still our lighting set up, but with a bit of noise. And let's also make it green. So just like before, I can multiply these two together, set it to multiplication. I don't think the order matters. And now we have green with a tiny bit of grunge that I can make more detailed, maybe a bit rougher. And now we have the impression of maybe grass or something like that. Before we wrap up here, let's actually use some of this logic we made to create a nice little BSDF node for us. So what I want control over is I want to keep the normals over here. I want to keep the color stuff over here, I guess, so we can choose the color. And lastly, we like our ambient lighting, where we can choose that with a single number with a value. That's kind of the overall brightness of the scene. This is also something I want to control, and everything else, yeah, the rest we can throw into a group. So select all, Control Control-G, and now we've reduced our whole setup to basically 3 inputs. We can totally name these, so hit N for the panel. Our vector thing is really the normal. Our A is basically the color, and then this you can think of as ambient light. This outputs, not technically, but we'll call it a BSDF. So if at any point I was to change the color, it does that. If I change the ambient light, it does that. And if I modify the normals, it will modify the normals. I'm going to, let's just use, no, let's keep it like this. I'm just going to pack this into a little section for our color. Take this, Shift P for panel, I think it stands for, and connect that to the color. Okay, I think we'll call it a wrap here. I definitely think that's good enough for this part. I'm happy with this. By the way, little tip to wrap up here. If you want different colors or whatever for different objects, it turns out that even with a single material, right? So I don't need to duplicate this material and for this one, make it red and all of this. It turns out with a single material, it knows which object is which by adding maybe the geometry node has this. So remember we use geometry node for the position here. Oh, by the way, I got to make sure I didn't duplicate this. So now this should show everywhere. We have the position, but it also has other things like the normal, the tangent. But what we care about is there's something called random per island. Little hard to tell, but you're going to see this one's gray, whereas this one is white. And it turns out that each island, so I'm just going to kind of duplicate this here, each island, each separate piece of geometry, it generates a random number between 0 and 1 to distinguish them. Another way to do this, if you don't want the island situation, which doesn't necessarily work with duplicating the same object because it basically has the same island, there's also a node called object info, whereas this gives us a per shading point thing for different objects. Object info just cares about the objects themselves. So if I look at location, I can have one object moving and it's the same for the entire object. I can extract data like the object, not object index, but I guess we'll just use random. And this also gives us a random number, but now it works with this, which is actually preferable for us. And if I want to generate different colors with this, so now we're introducing new nodes, we could either, we could just do something like combine X, Y, Z, where this is kind of the strength of the red. So you can see these have different amounts of red. But if I want to actually randomize the color here, we talked about different kinds of noises, right? Or different kinds of textures. We have noise texture, we have wave texture. Here's an interesting one. There's something called white noise. White noise kind of looks like this. I think by default it uses generated coordinates. You're actually not going to be able to tell. What this does is it's basically like TV static. Every shading point, even ones infinitesimally close to each other, get a random number between 0 and 1, which means no matter how much you zoom in, it's basically going to look gray because it averages out visually. But it turns out that you can also do this with color, so you can get chroma noise. And to me, this is important because instead of using generated coordinates, we can use a single vector, right? Or a single number to determine this. Let's actually use a single number. And you're going to see as I change this number, it's going to give the same color to everything because our white noise is evaluating at a single vector, only at 3.07, 3.07, 3.07. And because that's the same everywhere, it's going to give the same random number everywhere instead of using something like, I don't know, position coordinates where you can see each shading point is different, meaning that if I have different random values, I can use this as the vector to give different, luminances, but more importantly, different colors, okay? And this is going to vary for every single object. And by the way, if you want to alter this, all you need to do is just offset your random a bit, and each one's going to generate a different color. So let's say instead of our green, I connect this over here, I view our BSDF, and now we have, I don't know, this looks more like a old school Toy Story scene to me. Panel, which by the way, in the end menu, you can give it a name, so I'm going to call it color, and that shows up. This is our kind of color thing. By the way, I probably should have closed these windows. I guess you can make this 4-dimensional, which gives it a W slider. Think of it as a randomization slider. It's a 4-dimensional noise, kind of complicated. More simply, we can just vary our input right here to change the color. And this works with various objects. If I give them the same material, so I'm going to put a sphere here, maybe I'll put a cube over here, make sure to Control-L link the materials. And now we have, it's way more complicated than what we had before. I'll say that. Okay, so in this part, we created light itself. I guess let's do another part. Are we going to keep going? I don't know. So I'm pretty sure this is going to be the last part. We'll see if I'm inspired to do more. So we have our fake BSDF, and I want to take it one step further and add kind of custom normal mapping. I'll tell you what that means right now. So we have our custom BSDF, which is starting to look pretty similar to the diffuse BSDF. So here you can see the diffuse BSDF. It looks a lot nicer because there's shadows and all this. But what I want to emphasize is for color, we have color. We actually have ambient lighting, which diffuse BSDF doesn't, and we have a normal socket, which I want to modify. We don't have roughness, but we'll live with it. What is special about this normal socket, which is actually identical to the one we made, is it inspires the idea of using custom normals, not just the ones you get. So let me show you what that means. Imagine that we use the same color as before. So we have our same setup over here. I'm going to make the light a bit stronger because it's using the actual power. You're going to notice that this looks pretty plain, right? It has all this noise, but it's as if it's a perfectly flat surface, but there's no texture or detail or grunge in the actual normal mapping. What I mean by this is if I look at the normal coordinate, it's just blue because it is facing directly upward. So Z component is 1, X and Y are suppressed. Well, what I can do here is use this kind of noise texture from before to actually create more normal coordinates. So I'm just can use a node we haven't talked about yet. We're actually going to make this ourselves. It's called the bump node. It converts like value information into normal information. And I'm just going to connect this into the normal socket. And you can see all of the sudden, all we did is we changed the normals. You can see that there's actual like texture here. Let me make this even stronger. There's actual like kind of like textural something to this, right? So this is without, it's just kind of like perfectly flat. And then this is with. Now, while our plane is in reality perfectly flat, which means from the side view, it basically looks like this and has a normal direction this way. What I want to kind of fake is, let's say that this surface is a tiny bit rocky, like kind of microscopically detailed. The difference in this case is our normals are no longer just straight up. In fact, in this section, it's straight up. In this section, it's pointed a little this way, pointed a little this way, going a bit up. And as we remember, we're using the dot product as compared to the direction of the light to judge kind of the darkness or shading of every single point, which is going to look different if we modify kind of the height or the normals rather than just using this flat surface. In other words, if I have a height map that basically defines how rocky I want the surface to be, we need a converter that goes from height information to normal information, again, extracting these vectors that aren't really there. Well, the theory of this is actually quite simple, right? If I'm at the peak of this, in other words, it's kind of flat, the way I know it's flat is what I'm doing in my brain is I'm imagining this tangent line that's just tangent, it's right on the surface. And if I take this tangent kind of direction and rotate it by 90 degrees, we have the normal. Similarly, if I have a point that's on a bit of a slant, I imagine this kind of tangent line, I, have this vector, I rotate it by 90 degrees, and then I have this. In other words, to extract the normal vector in a case, this two-dimensional case, all I need to know is basically kind of this tangent line, which will give us the normal. Now, in 3 dimensions, it gets a bit more complicated, right? So instead of like, a two-dimensional rocky surface, it's kind of, so here I'm trying to draw a 3-dimensional hill. It doesn't really translate, but here the surface is 3-dimensional. So instead of a tangent line, we have tangent planes that are facing different directions, each with their own normal vector, which means instead of getting kind of like a simple slope of a line, we kind of need the slope in a sense of the surface, which actually generalizes quite nicely. In the 2-dimensional case, the way I actually calculate or approximate this tangent is if I have this kind of like height map, like I know what this hill is, I know the slope of this tangent by looking at rise over run. You might remember that. So we have y, that's the rise, divided by x is equal to the slope, or at least this is a approximation, because what we need to do is have this rise over run sampled at tinier and tinier intervals closer to our point, right? Because if we have a point like this that exists somewhere on the x-axis, so we have an x value right here, I'm going to sample a bit to the left and maybe a bit to the right. So I give a bit of a nudge on the x-axis. So let's say we're now evaluating right here. We look at the rise, the difference in the height between these points, and how much we traversed on the x. So you can think of this as x plus a tiny infinitesimal kind of like delta. So this will give a pretty good approximation instead of like, let's say we did a big shift in x. So this is x plus like a big delta. In that case, I'm like evaluating over here, and then the rise over the run kind of represents a very like different slope. So too, in 3 dimensions, we have a bit more leeway. So I can go in this direction, I can go in this direction. There's a lot of options. All I need to do is sample the x and the y direction and kind of combine them. So I'd go a bit on the x-axis, and then I sample and I look at that 2-dimensional slope, rise over run, and then I also sample, let's say, the orthogonal, like in a different dimension. I then say combine these to create the 3-dimensional slope or the tangent plane that then defines a normal. In other words, instead of a extra evaluation, I have to do an extra 2 evaluations. So for this, I'm actually going to take my noise texture nodes and just put them over here for now. We're going to use the original, but for now, I just want like to illustrate this more simply. This noise texture you can think of as a height map, and you're thinking, how is that height? It's just kind of the splotchy thing. Well, if I make this higher contrast, you'll be able to see. You can think of black areas as being on the surface, and the more white it is, so like a white point over here represents something that's higher up. In other words, if I have a rocky surface like this section right here is going to be black with a value of 0. This section right here is going to be 0.5, and as we go higher and more white, it eventually maxes out at a height of 1. So if I want to sample this at 2 different spots, or I guess, yeah, 1 on the x and 1 on the y plus the original, so 3 spots, all I need to do is I take my coordinate system and say nudge it a little, right? So instead of our default coordinate system, I can add a tiny bit on the x, right? Like 0.2. And you can see what this effectively does is it like moves our height map, which makes sense because I want to sample just a bit to the side, so I need to know what that is. So let's say I shift this by 0.1. So this is without and this is with, just a bit of a nudge. If I want to know the rise over the run, we can figure out what the rise is by evaluating again. So this is our original, this is our shifted. The rise is the difference between the heights, right? Like how high up did we go? So I subtract these. And then the run is how much I nudged it. Remember, our slope is the change of height over the change of how much we nudged it. In this case, we nudged it by 0.1. So literally take this and divide it by 0.1. And this piece of color that you're seeing here basically represents how much the surface is changing on the x-axis. So instead of going like 0.1, for example, I want to explicitly say, what do we go? Like 0.1, 0.2, 0.05, whatever it is, we divide by this number. So I'm going to divide by 2. So now this is going to be a bit more accurate. Divide by 2, a bit more accurate. accurate, and you really want this to be tiny. So saying 0.0001, which is what is actually written here, even though you can't see it, is better than 0.1. You're going to see these look pretty similar, but one kind of has more accurate data. So too, can we do this nudge on the y-axis? So all I'm going to do, oh, by the way, this might be responsible for the change. Make sure you're using object coordinates, not necessarily because they're object coordinates, but because we used them here. So if you use generated for both and vice versa. Actually, this looks a lot more sensical. It looks a lot more sharp. You can almost imagine the surface. Next, I'm going to do the exact same thing. So I'm going to take my object coordinates. I'm going to offset them by basically the same thing. So I have a custom vector, but this time, instead of nudging on the x, I'm going to take the same number. I want to nudge by the same amount so that they're, in terms of ratio, kind of like equal to each other in a way. Doesn't matter. I'm going to take this number and this time shove it on the y-axis, okay? So instead of x, we're doing y, which means we, again, have our original sample and our shifted y sample. You can barely tell the difference because they're barely different. I'm going to subtract the two, so we are comparing them. And then, did we do everything correct over here? I believe so. And we need to divide by this very tiny number to kind of normalize this. And now you can see we kind of have this rough direction. Let's actually view it from the top in this y. So you can almost see it's in this axis, and then x is the other. Like I said, if you combine these contributions, so this is basically a change of x in terms of slope, and this is a change of y. We combine these into a single vector. This is the x component, this is the y component, to get something that's kind of like a normal map. Really, this is the difference of what we had. To get the actual normals, you need to add the original contribution. So it's pointing up, and then we added a bit of variation. So you set z equal to 1, and this is the actual normal map. Let's see if it's identical to the way bump node does it. So I plug this into the height. You can see it looks basically the same. If you do not want to add the z component, which by the way is different depending on which way we angle the surface, instead it would make sense to use this difference and then add our original normal. So we have what it was before plus our contribution, which updates depending on the direction. Now, technically, we do live in a three-dimensional world, which means, yes, we can kind of approximate this normal using x and y and all of this, but that isn't accurate in any case where like this isn't like perfectly flat and we're doing a height, right? If we have a sphere, some tangent planes are pointing upwards, but some of them are pointing downwards. So you kind of have to account for all of these. So there is a sense in which you also want to do another evaluation. So now we're doing 4 total evaluations, and we do need to copy this noise texture each time or whatever height map you have. You can't just put it all in one vector. The cost of doing a normal is just doing extra evaluations. So this is going to be our object coordinates, you know, the drill plus an offset of this number on the z-axis. I subtract our new contribution minus the original. I take this bad boy and I divide it by our tiny number, which in the case of it pointing straight up, you can expect is just going to be, well, I guess noise texture is 3-dimensional in a sense. So you wouldn't really see this in like a 2-dimensional image, but in this case, there is a change of like z component, which will update depending on the direction of the surface. By the way, you can argue that we want to like make sure these are all in the same order. So for example, we do a shift in x minus the original. In this case, we want to do a shift in y, which is this one. So we need to flip it minus the original. And then in this case, we have a shift of z minus the original. Basically, as long as you're consistent, you'll be pretty good, plus or minus a minus sign. So we have our x component, we have our y component, and now we have our z component that gives us the total offset that, again, we can just add our normal to. So make sure we have our normal coordinates, and this is basically what is going on here. This whole nonsense we want to use for the dot product, basically. So because this is a monstrosity, we can take this and actually put it in a single node. Of course, we might change the height map later, but whatever. So I'm going to combine all of this nonsense, all of it, except for maybe this like 0.001 that I guess I do want to like change later. So I'm going to take all of this plus the coordinates, Control G, and all of that nonsense reduces to something that is actually manageable. The reason that node, by the way, is called bump is we are shifting the surface. And we don't actually need our original normal coordinates because we added them inside of here. Okay, what is the point of all this? The point is now we have our BSDF. I told you we'd go back to this. It's using normal coordinates, but here I have a different one where I can plug it in, and now you can tell it's a bit intense, but it's actually responding in a way that looks, you know, accurate, right? So now the question is, how do we take this and make it less intense? Well, we always want to have our original normal coordinates plus our calculation, but our calculation of adding in these fake normals can be not as intense, less contribution. In other words, you take this and you multiply it by a tiny number. You can think of it as just multiplying it. Again, you can use a value here by 0.1. So here you can see instead of 1, we use 0.1 and it's much softer. Another way to do this, by the way, that's more intuitive is you use scale. This is identical to multiplying by value, except this time the value is explicitly here. And we now have the luxury of making that a parameter where the first one is the distance of sampling and the second one is the strength of the normals. Now we didn't do all this work just to have a plane, right? We want to have the 3-dimensional case. So let's bring back our objects here. So remember we had this setup where it picks the color randomly, And because they're all using the same material, they all have that noise texture. And you can see it's looking much more realistic than before, right? It's capturing like more information in a sense. And this is kind of how like rendering works, or how BSDFs work. We just made our own. And the name of the game is basically swapping out our height map, which right now we're using this noise texture for whatever it is we want, okay? Because there actually is a bump node, that the difference between these two, well, we want the real bump node. Actually, the one we made is the real one. But the reason we want this bump node is instead of like putting in this noise texture or whatever height map 4 times, if I want to change it, I'd need to change it 4 times. This bump thing basically does that for us, okay? So I'm going to keep this off to the side. It is useful, but I'm going to use the standard now that we know how to make it. I feel like we've earned it. So now I plug this into the normal coordinates, and right now it's just using the normal. By default, it looks like this isn't connected to anything, but it is just using the normal coordinates. Instead, I'm going to use this like noise texture, for example, as the height. It's literally called height because it's a height map, and now we have basically the same thing where we control the strength. We just made this ourselves. It happens. And I guess in this case, distance is kind of inversely proportional to what we did. Either way, we now have a bump, which by the way, you can invert. So instead of popping outwards, it goes inwards, kind of like reversing the vector for the dot product. Doesn't really matter. By the way, I should mention, ideally, we do like vectors normalized to get them to work the way we want to in terms of the dot product. So you do want to make sure, I guess, at the end of this, you have your normal plus the contribution. Just take it and normalize it. So it has a magnitude of 1. This is important because our BSDF calculates a dot product and doesn't do the normalization in there. So we'll do it in the other one. Either way, we now have the luxury of swapping our height map. So let's do something different, like a wave texture that looks like this. You plug in either the color or the factor. I believe if you do the color, we'll just take the red or X component. I'm going to plug this into the height. It looks pretty much what you expect it to look like. And now you can see it's as if we actually modeled ridges into our surface. That is normal mapping, which is kind of like the big piece of kind of like realistic rendering here. And in a way, you can think of roughness or how shiny a surface is, not technically, but kind of as kind of like inversely proportional to our strength. So as the strength is big, not very rough, or sorry, extremely rough. Like there's not much reflectivity is what I meant. And then as this goes down, you can think of this as kind of more reflective. Technically, when you have reflections, you have a light ray hitting the surface. It looks at the normal and then goes this way and then goes this way and sees what it's actually reflecting. So like a mirror, it would have a bit of red, a bit of whatever. We're not doing that in the same way that we are not doing shadows. Here you have your diffuse BSDF. If you get rid of the shadows, there's actually not much of a difference. So for our objects in visibility, I can actually disable shadows so that we get, pretty much what we have set up over here. So I'm getting rid of shadows. And now you can see the diffuse BSDF in action compared to our custom BSDF, where I have to lower the strength of this, which looks pretty similar in my opinion. Again, the difference is it has like reflectivity kind of with the roughness, and it has global illumination where, this point in some sense affects this point because light can bounce and do all kinds of things. But that is our custom BSDF. Okay, I decided we're doing another one. This is the final part of the series because I think I've taken you from 0 to hero, right? There's more with image textures and all this, but this is kind of the basics of how things work. In this part, I mentioned reflectivity and kind of light bounces and all that. We're not going to do light bounces, but I am going to kind of do reflectivity for you guys. So at the moment, our environment, or we call it the world, is basically gray, right? There's not much to reflect. And by the way, we can totally change this either in the world parameters. Of course, this isn't going to affect anything because we want this to proportionally affect our like ambient light, but whatever. It turns out that you can do more than just pick a color, right? You can change it for all kinds of things. What you want to do is in the world settings, you can pick your own HDRI, which is basically an image that represents the spherical environment. If you have a node wrangler, you can hit Control T. It adds all these nodes. We basically know what these do. We know what generated coordinates are. We know what a texture is, although this time it's not noise or wave. We just pick our own image from our computer. And the mapping, we didn't really talk about, but you can think of this as kind of offsetting. So for location, which is really the only one we talked about, it's the same as just offsetting with a vector. So with a environment texture, what I can do is I can load a HDRI that I downloaded from the internet. This is our environment. Again, it's not going to be reflected, whether we have EV or cycles, like it's just not going to show up. But for now, I don't want to see that. We might turn it on later. I want this to kind of affect what we see, over here. So back into object land where we're dealing with our material, we somehow need, so like, let's say we have a reflection over here. We're viewing from the camera. So we are looking in from the camera. We have a ray from the camera going here. It's going to reflect kind of like infinitely into the distance until it hits kind of like our environment, our scene. And that tells us what it should be reflecting. Well, we need a way to kind of reflect things. And we can totally do this ourselves, right? We know how to calculate a vector coming from the camera. We actually did this ourselves. And it turns out there actually is a node for this. It's called incoming, because this is the vector that is incoming. It is coming towards the camera. It changes based on perspective. And you can totally reflect by saying, take the incoming vector, look at the surface normal, and just kind of reflect off that direction, like bouncing off a wall. We can totally do that. I guess let me just show you how you would do that. So we have our incoming, we have our normal, and just like we had cool operations with our dot product, so too can we take vector math and look at our options, and we have reflect, refract, face forwards. We care about reflecting. So if this is what I think it is, we take the incoming vector, we're looking at the surface and then reflecting it off of the direction of the surface, so off of the normal. This is going to give us a coordinate system that looks like this. Main takeaway is that it is view dependent, right? In this case, it's going to be one color because we are, reflecting off of something that has a consistent normal. Whereas if I was to kind of bevel this, you're going to see it kind of changes, okay? In a way, we've created what you can consider to be a reflection coordinate system. It just samples off into the distance. As always, there is a pre-established thing for this because this turns out to be quite useful. So if I look at my not normal, not UV, not object, but reflection coordinates, they're not necessarily going to be exactly the same, but you can see it does kind of a similar thing. So this is our custom reflection. If anything, it looks the same minus the black here. I think the main difference here is technically, so we know how to make a ray going from the camera to the surface. I said that there's something called incoming. I think what it is technically is it is that, but it is the inverse, right? So if I have a camera here casting a ray onto the surface, this is what we want, right? This is what we want incoming to be. But I think incoming technically does the opposite. I think it goes from the surface to the camera, which means I can just multiply this by -1 and it will give us what we want. So I take incoming, I vector math. You can either multiply or, like we talked about, scale by -1. Now it's going to be, the opposite. I use this over here. And now, is this the same thing? It might still be a bit different. Let's see. Our reflection coordinates theirs versus ours. Nope, it's the exact same thing. So we've calculated a reflection coordinate system, and it makes sense how we did that. At least it makes sense to me. Hopefully it makes sense to you. Once we have this coordinate system, we can say that the world, our environment, had any kind of texture that it's now sampling. So kind of an obvious example that we get for free, like we talked about, is this noise texture. So unlike before, and let's make this kind of higher contrast over here so we can see what we're doing. Okay, yeah, that looks pretty good. Unlike before where it sticks onto the surface, because this is view dependent with the incoming, you can see that this gives, a reflection, definitely for this ground plane. It looks like a mirror. You could swap this with anything. So let's do a wave texture. So now we have waves reflecting. It turns out that we can actually, just like we put in our world, a custom environment texture. So this is called a environment texture. It's not a normal texture. There is a difference. We could load one of those in. So with our reflection coordinates, let's load in not an image texture, but an environment texture. You're going to notice the differences other than the name, of course. The most important thing is this thing that says equi-rectangular. This is important. Let me show you, because if you look at an HDRI, it's a 360-degree image, but it has to be represented in a rectangle. And this weird distorted thing where this section, Pac-Man, teleports over here, this is just called equi-rectangular because it's a rectangle and it preserves area or something. I'm not sure. This has equi-rectangular, whereas this only has other kinds of projections. So in the environment texture, I'm going to choose this burnt warehouse, which by default kind of gives this weird kind of thing. Either way, this is not what we want. We want the reflection coordinate system. And now you can imagine, right, especially with this sphere, this is like a chrome ball, you can see the environment reflected. We can actually enable our scene again, and this should give us what we need. So in the ceiling, we have wood planks plus this sideways wood plank, and you can see that reflected. There's a reason the word is reflected. We need it to be in our kind of BSDF here, okay? So we know our BSDF has color that we then like shade with our dot product. I want to also include a hit of color from our reflection. So first of all, we have our color that I want to contribute. So we have our mixing and everything. So our mixing just darkens it or our multiplication. Before I do that, I want to mix it with another color. I want to tint it by a custom color. So I'm going to put an input over here. Instead of color, I'm going to call this, or maybe like world color or something like that. And I can move that above so that the color and the world color are together. I want to mix this with our thing over here. So not just the color, or not just the world, but the world using a reflection coordinate. So I'm going to put this right here. Let's view it. It's going to give us what we had before, but now with some reflectivity and still with our darkness. So it kind of just works, right? Like now we have something much more dynamic. Let me get rid of this, but this isn't technically probably the best way to do this. The reason for it is it's mixing the color and the reflection equally everywhere. It's the same on the edge. It's the same here. And in reality, that's not how it works. If you think about it, imagine you have, here's another analogy. Imagine you have a puddle of water, okay? Or maybe a lake. If I'm the viewer and I view the lake from over here, so I'm kind of standing on the beach, I'm looking at the lake and that is going to reflect this way or like upwards, and it's going to show maybe the sky or maybe some trees in the distance. However, when I look at it from the top, you might notice that when you're on a boat and you look directly down at the water, you don't really see much of a reflection. If anything, you kind of see into the water. You see the depth as it goes down, 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 getting darker into the surface. Whereas if you look from a different angle, you see the reflectivity. So it turns out that the surface normal versus our incoming vector, take a dot product, gives us, in some sense, maybe an inverse of how reflective it should be, right? So dot products are used everywhere, wherever we have a surface normal. Remember, did we end up using a Fresnel? We have a Fresnel that basically gives us exactly that, right? So in reality, if we look directly into the surface, like this part of the sphere, it's going to be black-ish, which means that it's not going to have much reflectivity, but on the edges, we get much more reflection. And we can control that. Beautiful. And by the way, I should mention, now that we have our custom normal coordinates, you're going to notice that Fresnel, just like anything else with a normal socket by default uses these coordinates, you can add our fake coordinate system, and in the Fresnel, you're going to see it adds that fake detail as if it was contributing to the view angle. So that's just a thing. But because we have our Fresnel, we can mix in our reflectivity that we can kind of say how intense is it also by this Fresnel. So I'm going to do that here. It's going to be quite subtle, but there is some reflection going on here. There is some reflection, and you want to make sure that the world color is in the bottom socket. So let's see. This is without, it's just color, and then this is with, and let's see if this does what we want. So if we look at this kind of like a hardwood floor from this angle, quite reflective, but as I look up, no longer reflective, and we can see that in the cube. We can have this IOR, which remember is affecting the reflectivity. It's also affecting this kind of like addition we did over here, or was it a multiplication? I don't know. We just added like a bit of something. We can make that a parameter. So now IOR is here. IOR is different for different surfaces. It turns out water has 1.33, whereas glass has 1.5, whereas other things much higher. You can think of these as metals. I'm going to keep it at 1.5. We have our nice reflections with our nice lighting. Kind of the last thing, kind of the last piece of the recipe I think we're missing is if you look at the reflections in a diffuse BSDF, or I guess actually, let's do a reflective one. What's it called? I think glossy. So glossy BSDF gives us the reflections. You're going to see that it kind of scatters or diffuses the reflection, unless I set the roughness to 0, where we have what we had before, right? Nearly identical except for the reflections of the objects themselves. But the main thing we are missing is kind of this roughness. How much does the thing scatter? Well, here I'm going to show you a trick. So you can think of scattering of light, of a texture, of whatever, as basically blurring it approximately. I don't know if that's true, but you can think of it as blurring. So if we can make a blurring node, we can kind of fake roughness here. So I want you to imagine, not an image texture, I want you to imagine we have a very, kind of like very visual texture, like a Voronoi texture, which has all these cells. If I want to blur this, it should kind of look like fuzzy on the edges, and in fact fuzzy everywhere. Now the question is, what is blurring? Well, if I take this point on the edge, ultimately should be kind of the average of everything around it. The way that works is for this point, it samples a bit over here, and then it samples a bit over here, and actually it samples in every direction, and for each one it says, oh, this is orange, this is orange, this is cream, and for every sample it adds and averages them out together. But our blurring is more effective the more kind of directions that we sample. So somehow I want to sample this in every direction and blur it and all of this. There is a node that we actually already talked about that does this. What is it? Well, remember that our, whatever texture usually by default uses generated coordinates. What I want to do is we already know how to sample, right? We just shift it a bit to the side like we did with our normals. I want to shift it, but kind of like everywhere. Of course, that's not possible because we can only pick a single direction at a time. But if you look at this like cluster of points that kind of represents this one, if every single point inside of here kind of picks a different one and they're so close together, it will look about right. Well, how do we like pick random directions? How do we know how to do that? Well, remember when we were randomizing, we used this thing called the white noise texture, which if we use generated coordinates, gives us a number between 0 and 1 on every single point, no matter how close together. But so too can we pick a random color, a three-dimensional X, Y, and Z vector, which we can think of as a direction. This is a way to sample random directions, right? It gives us random things. So if I sample this way, like I do a bit of an offset, you're going to see that it looks kind of ridiculous, right? Because we have our generated coordinates and then I'm adding this massive blur. Well, I can take this contribution and basically make it less intense the same way that we made our normal, custom normal contribution less intense. So as I scale this down, let me set it to 0, we have this, and then as I shift it, you're going to see it blurs. But you are going to see a bit of an issue. You're going to see, yes, it blurs, but it also kind of goes off to the side as if it's kind of being pushed diagonally. So it's being pushed downwards and diagonally. Why is that? It should be picking random directions. On average, it should not really move. If you think about it, if we're picking a random direction, right, that's not actually that. It's really just a number between 0 and 1. But on the X, Y, and Z, like we have 3 random number generators that go between 0 and 1. That means that on average, if you average them all out, it's going to pick a number, basically that's 0.5 on average. This means that on average, we are shifting our coordinates by 0.5 on X, Y, and Z multiplied by our scale. Of course, we don't want this sampling from 0 to 1, but instead we want it centered. So you can think of it as instead of 0 to 1, we can map range to -1 to 1. Did you know you can take a map range and instead of a float, you can use a vector, which is basically the same thing as a color. You take a input interval and you send it to an output interval. So it's going from 0 to 1 on X, Y, and Z, and we want to map it to -1 to 1, just so it's centered. And what you're going to see now is it's not blurred, and as we increase it, it blurs quite intensely actually, but it does it in a way that's uniform and stays centered. Now, the reason this blurs so incredibly fast is the directions these are sampling isn't just like this way, but it's this way with a giant magnitude, right? Trying to kind of solve that by bringing down to scale, but some of these can be pretty big. If you just care about the direction, we know we can normalize. So this is without, this is with, going to be kind of subtle, but it will kind of work here. What was the point of this? We wanted it for blurring our reflection texture. So for now, I'm just going to add a empty thing. The reason I'm doing that is I want to highlight Control G. You need to have an output for this to actually, come out with this vector. What I mean by this is if I didn't have this here and I Control G, there would be no output. So Control G, I'm going to call this like blurring in some sense. And we don't just want to blur necessarily the generated coordinates, although often we do. I want to blur a custom coordinate system, okay? So this is going to be blurred coordinates, and this is going to be our coordinates. So we input coordinates, we output blurred coordinates. So ultimately, we have our reflection image. I'm going to pass this reflected coordinate system through our blurring. And is it perfect? But we've essentially blurred, and you can see these bokeh balls. Let's add a parameter, of course, for how strong this is. And instead of doing this directly, where the numbers have to be very small, let's divide it by, let's see, if we have 0.03, let's divide it by 10, for example, which means 0.03 effectively becomes 0.3. As we increase it, it gets very diffuse, and as we decrease it, it becomes quite sharp. And you can use this blurring for all kinds of things that we did before. But either way, I view this now. We indeed have our reflections, which I might want to see more of or less of, but I can also control effectively the roughness of those reflections. So 0, 1, it ain't perfect, but it's an honest living. I guess kind of like a final thing to note is we have control over where the reflection appears, how rough it is, but we don't have like a general strength slider, I guess. So we are like using the Fresnel here, but what if I want to take this Fresnel and kind of modify it? Well, we can either kind of modify it with a multiplication. So as I increase this, it kind of gets some more metallic, and as I decrease this, it kind of gets more diffuse, or you can think of it as a addition where it's uniform. I think obviously multiplication makes more sense. So I'm going to call this reflectivity, right? So now our reflectivity is at 0. We can increase it, and now it's more reflective. If I wanted it to be a nice metal, I'd pick kind of like a darkish color with high reflectivity and maybe a low blurring. And yeah, let us do just a bit of experimenting. We don't need to have this HDRI. We could have picked this outdoor forest one that I actually want to see. And let's actually also bring down our reflectivity so we can see all of this, maybe 0.5. Maybe let's bring down the IOR and bring up the strength of our normal coordinates. I mean, you know, you can't get better than that. So what have we done in this tutorial series? Just to recap, we can go further, maybe. I don't think I want to at the moment. We went from basically going with a single value node. We just talked about what is a number? What does it do? How does it represent a kind of surface output? We then talked about vectors, colors, how to like multiply, how to use dot product, and use all these methodologies to basically recreate the diffuse BSDF, but fully custom with the drivers that let us kind of pick our lighting nicely. So we created essentially what we call a BSDF. Really, this is just a shader that responds to lighting and reflections and all of this kind of stuff. So I hope you enjoyed this tutorial series. Where do you want to take this from here, you might be wondering? Probably the next step is going over other BSDFs and talking about transparency and all of this. But what we were building to is kind of recreating the granddaddy of BSDFs, which is the principled, right? It has this metallic, which you can think of as our reflectivity, kind of makes it more metallic. It has roughness, which you can think of as our blurring. It has IOR, color. We're kind of building towards that. It has normals, but what it's missing is it doesn't have emission. We don't have transmission. So hopefully you learned something. That is what I know for kind of like a level 1. If you want a level 2, maybe beg and maybe I will do it. The man puts on his hood in mystery as he creates the best tutorial of all time.